I think we're a little bit limited by restricting our attention of postsynaptic singles to opening and closing ion channels and EPSCs and IPSCs. Yeah? Of course, that's one thing that these transmitters do. And that's the privilege that you have if you're an electrophysiologist. You can measure that. Fantastic resolution in time, fantastic resolution in space. But do we really think that's the only thing these transmitters are doing? I think many of them they're going through G proteins, they're changing gene expression, they're having much longer term effects. Philosophical point of view, electrophysiology went through a fantastic period in the 60s and 70s because its resolution is absolutely superb. The signals are clear and loud. But we used to think that channels were just like, that the only important part of a channel was the hole down the middle. In fact, we now know that transmitter through a receptor can go to huge signaling complexes of proteins which are associated with the channel. You may change expression of the channel in the membrane. You may signal downstream into the nucleus and change gene transcription. It's just that the ones that we were focusing on for so many years were just the hole down the middle of the channel because we can measure the ions that go through it so easily. And the thing that broke open the field, I suppose there were two things. One was for the nicotinic receptors, and this was Numa's work in Japan of cloning nicotinic receptor subunits. Somehow, for the first time in 1983-84, people recognized that you could get a feel for what these proteins looked like. And then later, in about 1987-88, Lily Jan isolated cDNA for a Drosophila potassium channel. And for the first time, we had an idea of what a potassium channel was like. As soon as we saw Lily Jan's paper, John Edelman and I immediately cloned the mammalian potassium channel. Because as soon as you've got one bit of sequence, then you can use this as a basis for homology-based cloning approaches.